There is often more than one way to solve a mathematical problem, and sometimes one way is easier than the others. Usually the easier one has been discovered after people have spent many hours and even years calculating the slower way. And that is true with linearization and Newton's method. Hi, my name is Tom Atwater, and that's what we'll be exploring in today's lesson. Let's start off with a definition. We have the definition of linearization, and it says if f is a differentiable function at x equals a, then the equation of the tangent line, capital L of x, is equal to f of a plus f prime of a times x minus a. And that defines the linearization of f at a. The approximation f of x is equal to capital L of x is the standard linear approximation of f at a. The point x equals a is the center of the approximation. Let's try an example of this. So A, find the linearization, capital L of x, of f of x at x equals a. Then answer, how accurate is the approximation, capital L of a plus 0.1 equaling f of a plus 0.1. The function f of x is equal to x plus 1 over x, and remember, that's for a equals 1. So what we're going to do here is plug this into the formula, and that means that we need to take the equation and find its derivative. So we have f of x equals x plus 1 over x. F prime of x is going to equal, well, the derivative of x is just 1, and the derivative of 1 over x is negative 1 over x squared. So we need to find two things. We need to find f of 1, and we need to find f prime of 1. Let me do f prime since it's set up for me. That's equal to 1 minus 1 over 1 squared. So it's 1 minus 1, which is 0. Let's take and find f of 1. F of 1 is going to be equal to 1 plus 1 over 1, which is 1 plus 1, or in other words, 2. Now we need to find the actual linearization, capital L of x. We have all the information we need to plug into that. So we have L of x is equal to, and we have to do f of a, which is f of 1, and we said that f of 1 was equal to 2. Then plus f prime of a, which is f prime of 1, which we said was equal to 0. Then times x minus a is 1, so it's x minus 1, and then that, of course, is equal to 2. So our approximation, L of x, is equal to 2. Part B was to determine how accurate the approximation for L of a plus 0.1, which is L of 1 plus 0.1, in other words, L of 1.1. So L of 1.1, well, it actually doesn't matter because we found that L was a constant term, so that means that it's equal to the 2 that we discovered over here. We want to compare that to f of 1.1. And when you plug that into the original problem, which, remember, is up here, we plug in 1.1 and 1.1. When you work all of that out, it equals 2.009. And what that means is that it's off by a little bit, but it's off by less than 1/100th, which is pretty accurate in terms of looking at what we have here. Now what I want to do is take a look at Newton's method. Newton's method is also a method for approximation, And in this diagram, we can see that what's happening is Newton says you take some kind of a first approximation, which right here, a first approximation, and it is given by the slope of the tangent line. And then what happens is we use that approximation to find a second point, which then brings us a little bit closer. And we use that approximation to find a third one, which brings us even closer, and until we use yet another approximation until we get to the actual root sought. Well, that's a diagram of the way Newton's method works. Let's look at how we would do it in terms of analytically. The procedure for Newton's method says, 1, you have to guess a first approximation because we have to start someplace. So you guess one that's a solution to the equation f of x equals 0. A graph will sometimes be helpful to find a first approximation. Then use that first approximation to get a second one, and the second one to get a third one, and so on, using the formula that the approximation x sub n plus 1 is equal to the x sub n approximation minus the function of x sub n divided by the first derivative evaluated at x sub n. And so we do that approximation over and over again, and it will get closer and closer and closer to the root that we're seeking. Let's try an example of this. Let's say that we have to use Newton's method to estimate a real solution to the equation and make your answer accurate to 6 decimal places, and the equation that we're going to use is x cubed plus x minus 1 equals 0. I'm going to show you a way that you can plug this into the calculator and have the calculator do those calculations for you. So you start off by entering whatever the function is in the equation editor y1. You enter in the derivative to y2. And depending on how complicated the y1 equation is, you can always use the n derivative function to find the derivative for y2. If it's an easy one to calculate, then you can do that yourself. Then on the home screen, you store in the initial guess that you made for x. Then you type in this formula right here in the home screen. That is x minus the first equation, y1, the first variable, y1, divided by y2. So this is, of course, your first guess approximation. This is f of x sub n, and this is f prime of x sub n. And then you store that into the new value of x. You press the enter key over and over again, and you will see that the numbers will begin to converge to the root or the 0 of f. On your calculator, when the values stop changing, it means that your calculator has found the 0 to the extent possible of the digits that it can display. So let's do that right now. Let's take that equation and let's plug in. In a moment, you'll see where I came up with the 0.68, but that's what I stored in for the first approximate value of x. Then I plugged into the calculator the x minus y1 divided by y2 and say, when you get that answer, store it back into x. So the first approximation it gave to me was right here, 0.68233, etc. Then I hit enter again directly, and it gave me this. And you'll notice that when I hit enter a third time, that it gave me the same display, which again means that the calculator has reached its limit in terms of the number of digits it can display. All right, let me show you the graph, because the graph will show us why I picked the 0.68 as my first approximation. Of course, with graphing calculators now, you can actually get a very good answer. And I'm not sure if the calculator uses Newton's method or if it has its own method of solving for these. But you'll see this is why I picked 0.68. I just truncated those last digits after it and used 0.68 as my first approximation. So that's how you can use your calculator to calculate Newton's method of approximating the roots. Okay. Next, I want to look at a definition for differentials. Let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals f prime of x times dx. Let's try an example of using this formula so that you can see it clearly illustrated. Let's take and say that we want to find dy and then evaluate dy for the given value of x and dx. And the equation that we're going to do this, or the function that we're going to use, is y equals x squared times log x, where x is equal to 1 and dx is equal to 0.01. So the first thing we want to do here is to calculate its derivative. So the first derivative of x squared log x means we have to use the product rule because we're multiplying two functions. So we take the first function times the derivative of the second function, and then add to that the second function times the derivative of the first function. So this is my dy dx, my y prime. According to the formula that we just looked at, dy is equal to the derivative times dx. So what I would have is x, of course we can simplify that to x, times dx, plus, and I'm going to rearrange these so there's no confusion, 2x times log x times dx. Now I can evaluate my dy because I have all of the information I need given to me. X is 1 and dx is 100th. So dy is equal to 1 times, actually let me put that in parentheses, 1 times 100th plus 2 times 1 times the log of 1 times, and I'll put that in parentheses, the 100th. And when we work all of that out, remember that the log of 1 is equal to 0, which means this entire term is 0. So dy will equal 1 times 0.01, which of course is just 100th. We often use differentials to estimate change. There are 3 types of changes that we can find. So let's take a look at each one of them. First of all, we're called absolute, relative, and percent change. Let's look at absolute first. Absolute says that the true amount of change is the delta f of x equals f of a plus delta x minus f of a. But we can estimate that change by using df equals f prime of a times dx. So that will be an estimation of the true change. So that's absolute change. Let's take a look now at relative and percent change. My setup is a little bit different. I have relative change and I have my true change and my estimated change. So for relative, the true change is delta f of x divided by f of a. And the estimated change for that is df over f of a. So df divided by f of a. For percent change, all you'll notice is that you multiply both of the relative changes by 100. And that's the relationship between the relative change and the percent change. Let's try an example of this. Let's say that we have the following word problem. In the late 1830s, French physiologist Jean Poiseuille discovered the formula we use today to predict how much the radius of a partially clogged artery has to be expanded to restore normal flow. His formula, V equals K times R to the 4th power, says that the volume V of a fluid flowing through a small pipe or tube in a unit of time at a fixed pressure is a constant, K, times the 4th power of the tube's radius, R. The question is, how will a 10% increase in R affect V? Well, remember, changes are with respect to our first derivatives, and so that's what we'll use in this problem. So let's take V is equal to K times R to the 4th and work with that. What we know is that the derivative of V with respect to R is going to be equal to 4K times R cubed. So that's my derivative of the volume with respect to R. Now, what I'm interested in here is that we have dV, which is equal then to 4K R cubed times dr. All right, so we're interested in that dV. Now what I want is, how does that change in the volume affect the overall volume? So dV divided by V. So that's going to be equal to my 4K R cubed times dr over the original volume, which is K times R to the 4th. So what we see here is that the K's cancel, and in terms of the R's, the entire R will cancel out all but one of the R's in the denominator, so that my answer will be equal to 4 over R and times dr. And what that means is that we will get a change of 4 times the change of R, and that means that a 10% change will actually produce a 40%, 4 times as much, 40% increase in the flow. All right, well, now it's time for you to try a problem. And the problem that I would like you to do is this. Minting coins. A manufacturer contracts to mint coins for the federal government. The coins must weigh within 0.1% of their ideal weight. So the volume must be within 0.1% of the ideal volume. Assuming the thickness of the coins does not change, what is the percentage change in the volume of the coin that would result from a 0.1% increase in the radius? Pause the video while you work on this problem, and when you're finished, restart the video to check your solution.
3.
Let's find out how you did on that. What we need to do is write down the volume of what a coin would look like. And a coin is really a flat cylinder, right? It doesn't have much height to it. But it is the formula for a cylinder, which of course we know is volume equals pi r squared h. And we want to find the dV, the dr, which is equal to 2 pi r times h. And remember, h, we were told, is going to remain constant here. So that means dV is equal to 2 pi r h times dr. And now what we want to do is find the change with respect to the original amount. In other words, we want dV divided by V. So we know that dV is 2 pi r h dr. And we know that the volume is pi r squared h. So we can cancel some things out here. We can cancel out the h's. We can cancel out the pi's. And then notice that this r can take out one of the r's in the denominator. So our answer will be 2 over r dr. And what that means then, of course, is that the change is twice as much. That is, the volume changes 2 times as relative to the change in r. So if it's a 0.1% change, then this would it will produce a 0.2% increase in the volume. All right, in today's lesson, we learned about linearization and Newton's method. Be sure to work the exercises that your teacher assigns, and we'll see you next time.